In this topic, we're going to look at complex numbers. Now, the first thing to remember about complex numbers is that they're not complicated. Right? There's nothing difficult about complex numbers. The complex really just means that they're made out of two parts. Now, it is a little bit of a strange idea. The basic thing is that we imagine a number. Now, you have been told in the past, no doubt, that there's no such thing as the square root of -4, because you can't square a number and get -4. Or there's no square root of -1, because when you square a number, for example, if you square -5, you'll get positive 25. If you square 5, you'll get positive 25. It's always a positive number. However, what we do in complex numbers is that we imagine a number that when we square it, gives you a -1. Right? So we imagine a number, we call it I, which when squared gives you -1. Now, I know it seems like a strange thing to do, but in fact this is one of the most useful bits of mathematics that you can do. It's used a lot in electronics, it's used a lot in physics. Whenever you have, in particular, any kind of periodic functions, sines, cosines in the future, you can often use complex numbers to make the calculations more simple. Now, for the moment, we can just treat I exactly the same as some other letter like X. So, bearing in mind that I is equal to the square root of -1, if you have the square root of -4, that's the same as the square root of 4 times -1. Split those out, so you get the square root of 4 times the square root of -1. Square root of -1 is I, so we're left with 2i. 2i times itself gives you -4. Similarly, if you did 5i times itself, you would get 25 times I squared. The I squared would be -1. Right? That would then be -1 times 25, -25. And if you've got something that's not a nice square number, like 17, you can just write I times the square root of 17 as a square root. Now, all those things up here, all these things here, 2i, 5i, and I times the root of 17 are all imaginary numbers. Complex numbers are made out of a real part and an imaginary part. So, if you have 5 minus 7i, that's made out of a real part, the 5, and an imaginary part, the -7i. Complex just means made out of more than one piece, a real part and an imaginary part. Now, the standard form is like this, where you can see the real part and a number times the I. So this example down here, it's not in standard form at the moment. What we've got to do is make the second fraction here look like something times I. And to do that, it's fairly straightforward. You multiply that second fraction, the top and bottom of the second fraction, by I. Now notice, now that the I squared on the bottom is going to be equal to -1. So the next step would be to replace the I squared with -1. In fact, the basic rule of complex numbers, as far as you're concerned, is wherever you see I squared, you can replace it with -1. Okay, if we then simplify that, we'll get 5 plus 3i. Now again, in the second question, we've got an I on the bottom there. To get rid of the I on the bottom, just multiply, again, the top and the bottom by I. We'll get this. Again, the I squared. The I squared on the bottom here can be replaced with -1. The I squared on the top can be replaced with -1. And if you do that, you'll get this. And that will simplify to this. Now, in example 2 on the second page, we do a very, very similar collection of things. Really, in these examples, just treat the I exactly the same as you would treat x, but then whenever you see I squared, replace it with -1. You might want to try that, pause the video, try that, and then look at the video once you've tried it. Okay, you can see how this is going to be simplified. We get 8 minus I in the first example. In the second example, remember to distribute the -1 before the brackets. We get 3 plus 7I. In part C, multiply things out exactly as if the i's were exactly like an x. If you do that, you'll get this, which simplifies to this, which then simplifies to this. Notice, if you didn't before, that the I squared here, you can then replace with a -1. -1 times -8 gives you +8. Now in this next piece, we have to define something called the conjugate, the complex conjugate. If you know that 2 plus 3i is one solution of a quadratic equation, 2 minus 3i is going to be the other one. This number here, -4 minus 7i, is the complex conjugate of -4 plus 7i. The thing to notice about that is that if you multiply the conjugates together, a plus bi times a minus bi, what you'll get is a real number. And that's useful if you want to put things into standard form. There's an example here where we have a fraction which is not in standard form. We have to get rid of the complex number on the bottom. To do that, multiply top and bottom not by 3 plus 4i, but by 3 minus 4i. Multiply top and bottom by that. Very quickly, if you do that, what you should get is this. Notice that on the bottom now, we have 3 squared plus 4 squared, which is a real number. It's not a complex number any longer. Simplifying it a little bit on the bottom gives you 25. On the top gives you -14 minus 23i. And then finally, if you want it in standard form, it should look like this. Now on the last page, we should notice that if you have something that's -3, square root of -3 times the square root of -5, that's I root 3 times I root 5, which is I squared root 3 root 5, and the I squared is -1, root 3 times root 5 is root 15, so the answer for this thing would be root 15. And notice that if you had square root of -3 times -5, it would be the same as the square root of 15. So this rule doesn't work if these two things here are negative. So whenever you're multiplying radicals together, radicals like this together, write them first in this form and then multiply them out. In example 4, we're just going to multiply out these brackets as they are here. But before we do that, let's write the square root of negative 12 and the square root of negative 3 in terms of I times something. So if we do that, we'll get, first of all, something that looks like this. This is just the first step towards this, where we've just written the square root of negative 12 as 2 times the square root of negative 3. Not strictly speaking necessary to do it like this, but you can do. The next step would be to say, okay, the square root of the negative 3 we can rewrite as I times square root of 3. The square root of the negative 3 here is I times square root of 3. Then we can multiply these two things together once they've been simplified. If we do that, what we should get is something complicated looking like this, but a lot of the complications will disappear. This I squared here is really just negative 1, so we can rewrite that like this, and then we can just gather together the real part. The real part is 10, and then this part over here. If we do that, we get 16 plus 8I root 3. And then there's just one last thing about complex numbers that I would like you to know. Whenever you have a quadratic equation, sometimes if the discriminant is negative, remember the discriminant is b squared minus 4ac, whenever you've got a quadratic equation that looks like this. If it's negative, we will get complex roots. I know that when we did quadratic equations in the past, we always just said there are no real roots. It's not possible to solve them, but we can get complex roots, and it's actually possible to get these on your calculator as well. If you want to solve a quadratic equation like this one, x squared plus 4 equals 0, that's reasonably easy to solve. You can imagine what you have to do here. You write it as x squared equals negative 4. So x has to be equal to plus or minus the square root of negative 4. What's the square root of negative 4? Well, it's got to be 2i. So our solution there is going to be plus or minus 2i. In the second example, we're a bit more adventurous. We have to use the quadratic equation. The quadratic equation we have down here. Notice that we've got square root of this triangle. This triangle is called delta, and it just represents the discriminant. So it's square root of b squared minus 4ac. That's what this triangle here looks like. If we do that, in this example here, our a is 3, our b is negative 2, and our c is 1. If we put those into the equation, we'll get this. If we then simplify that, we'll get this. The square root of negative 8, we can simplify to become 2 root 2 times I. And we could just leave it like that, but often we like to simplify that, and we could simplify it to 1/3 plus root 2 over 3 times I. Now notice, that's not the only solution. We've got plus or minus there. The other solution is going to be 1/3 minus root 2 over 3i. And you should notice, I hope, that those two things, those two answers that we have here and here, those two things are conjugates, complex conjugates of each other.